In the second video of our series on acid-base reactions, we'll look at how we can determine acid strength, not from a pKa table, because we won't always have a pKa table handy, and not every structure that we're going to look at is in a pKa table. So what we'll learn now is trends in acidity, and we'll start to build some chemical intuition about relative acidities. This way we can look at two structures and predict which is more acidic, based on the features of the molecule itself. So first, let's remind ourselves that as we've been discussing acid strength with pKa values, we've said that a strong acid is more willing to donate its proton than a weak acid. And that's because in a strong acid, the resulting conjugate base is more stable. And this is usually because the negative charge that results when the acid loses its proton is more stabilized. And the negative charge or the electron density can be stabilized in different ways. And that's what we'll look at here. First, it can be stabilized by charge. Let's compare these two acids. One is charged or cationic and the other is neutral. And let's look at the conjugate base that results when each of these acids loses its proton. In the top case, the cationic acid loses its proton to form a neutral molecule, while in the bottom case, the acid loses its proton to form a charged or anionic molecule. In the neutral structure, the electron density is more stabilized, and so losing a proton from the charged acid is more favorable, and so the charged acid or the top acid is more acidic. Electron density can also be stabilized by the element that the acidic hydrogen is bonded to. If we're comparing two acids with the electronegative element coming from the same row, then the more electronegative element of the two will better stabilize the negative charge that results from losing the proton. In these two cases here, we'll draw out the two conjugate bases that arise from proton loss. And then we can compare them. Nitrogen versus oxygen. Oxygen is more electronegative than nitrogen. It wants to pull those electrons in more tightly. And so a negative charge will be more stabilized on oxygen, the more electronegative atom, than on nitrogen. That means that the alcohol is more acidic than the amine. If we're comparing two acids with the electronegative atom coming from the same column in the periodic table, then we'll look at the atom size. And again, as always, we're thinking about what will most stabilize the electron density of the conjugate base. So comparing atoms in the same column, the larger atoms will pull that electron density in more tightly and stabilize it more than a smaller atom. So the smaller atoms will result in less acidic acids. So here, comparing the alcohol to the thiol, let's draw out the conjugate bases and then compare the two conjugate bases. In the case of sulfur, the electron density is more stabilized, so the thiol is more prone to losing that proton, and the thiol is more acidic than the alcohol. The larger atom leads to the more acidic acid. The last effect that we'll look at are polar effects. Polar effects in acid are the effects on acidity from further away in the molecule. And they can be from things like resonance or electronegative atoms, as we'll see in a minute. And so in these cases, we're comparing two acids where the atom bound directly to the acidic proton is the same. First, we'll look at resonance effects. Okay, here we can compare ethanol with acetic acid. We draw the conjugate base that would result from proton loss and then compare those two conjugate bases. And what we find is that in the case of acetate, we have resonance that involves that negative charge. And that resonance stabilizes the negative charge. And so acetic acid is more prone to lose its proton than ethanol because the resulting negative charge is stabilized by resonance. This makes acetic acid a stronger acid than ethanol. Another type of polar effect that will influence acidity is inductive effects. These are the influence of nearby electronegative atoms that help stabilize the negative charge by withdrawing electron density through the bonds. So comparing a series of alcohols where we have no electronegative atoms, then a chlorine, and then a fluorine, The case on the right with the fluorine will be the most acidic because the electronegative atom inductively stabilizes the charge that results when the acid loses its proton. Finally, differences in hybridization can also influence acidity. And in general, more S character of the atom that bears the negative charge leads to greater acidity. And that's because electrons are held more tightly in S orbitals, and so the negative charge or electron density of the conjugate base is more stabilized by that S character. So alkynes will typically be more acidic than alkenes, which are more acidic than alkanes. So now we've seen a lot of factors or structural features that influence acidity. Let's take a minute to try a concept check based on those ideas. Comparing the two structures shown, which is more acidic? And I've drawn in the acidic hydrogen just for clarity here, but note that no other hydrogens are drawn in. Okay, if you don't know where to start with a problem like this, always start by drawing the conjugate bases. Then you'll probably remember that you need to compare the conjugate bases. So I'll invoke some random base B to deprotonate the acids. And right away, when I deprotonate the first acid, I'll see that it's an acid with resonance. In the resulting structure, I have a negative charge, and I can put that negative charge on the carbon, or I can resonate it up into the carbonyl and put the charge on the oxygen. Okay, now let's look at the acid on the right. When we deprotonate it, we see that it too has resonance. So this question is all about resonance. Once we have our structures drawn out and we look at them again, we'll see that the structure on the left has two resonance structures. But the structure on the right, which has two carbonyls, has in fact three resonance structures. Okay, so the increased resonance of the structure on the right means that this acid is more acidic than the one on the left. The negative charge is more stabilized by the additional resonance. We'll end this lecture series with the question we posed at the beginning: to determine the products of the acid-base reaction, to identify the acid, the base, the conjugate acid, and the conjugate base, and to depict the flow of electrons and the direction of the equilibrium using the appropriate aeroformalisms. To start, I need to figure out which of my reactants is the acid and which is the base. And I can do that using our trends. Sulfur is larger than nitrogen and is to the right of nitrogen in the periodic table. So sulfur should generate the better acid because sulfur is better able to stabilize the resulting negative charge in the conjugate base. Okay. I could also look at the pKa values of these two species, and I would find that the pKa of the thiol is about 10, while the pKa of the amine is about 35. So again, we would end up with the same conclusion that the thiol is the better acid and the amine is the base here. That means that the nitrogen lone pair will attack or abstract the thiol hydrogen. So we can draw a curved arrow from that lone pair to the hydrogen. And then the electrons in the sulfur hydrogen bond will move to the electronegative sulfur atom, making an anionic sulfur. Okay, because the sulfur hydrogen bond isn't drawn out here, I'll start my arrow right between the hydrogen and the sulfur very carefully to indicate the electrons are coming from that bond. Okay, our two reaction products then are the ammonium salt and the thiolate anion. And the ammonium is the conjugate acid and the thiolate is the conjugate base. And we've now answered 3 of the 4 questions posed. We just need to determine which side the equilibrium will favor. And to do that, we need to compare the strength of our acid and our conjugate acid. That means comparing the thiol and the ammonium. And if we follow our acidity trends, the ammonium is charged while the thiol is neutral. So we should predict the ammonium to be the stronger acid, meaning the equilibrium will lie to the left or toward the weaker acid. So we'll make our left pointing arrow larger, and our right pointing arrow smaller.